section 6.2, the introduction to a differential equation. So what are differential equations? They're basically equations that involve an x, a y, and the derivative of y in some fashion. We're going to look at two different kinds of forms here that we're going to be used, that will be used in word problems. If they say a direct variation, so if you see the words y varies directly as x or y is proportional to x, then they are referring to an equation that looks like this, where y equals some number times x, or f of x equals some number times x. That number k is called the constant of variation or the constant of proportionality. If it's called indirect variation, then y will vary inversely as x, or y is inversely proportional to x. And it will look like a fraction where the x is on the denominator. Okay? We're going to use these variation equations to write some differential models that come up a little bit later. So keep those in mind. Let's look at an example of something that you'll be asked to do in some fashion. So here we go. So Catherine runs around a linear path. Her position is given by the function p of t, where t is measured in seconds since she started running, and p is measured in miles. During the first second of her run, Catherine's acceleration is proportional to the cube root of the time since she started running. Write a differential equation that describes this situation, where k is a positive constant of proportionality. Okay, so a differential equation, or they could have written it as a differential model since this is mimicking a real-life scenario. So the key words here, we're going to write the acceleration is proportional to the cube root of the time. So there's the key phrase right there, proportional. That means we're going to be doing this one up here, y is proportional to x. It will look like this, y equals some constant times x. Okay, so what are the two things we're talking about? Well, we're talking about acceleration. The acceleration is proportional to the cube root of time. So that's the key to this. So if I was going to write this out, then I can write this answer right here. The acceleration, which is the second derivative of position. So there's the derivative right there, the second derivative of position, is the constant times the cube root of time. Okay, when you write a differential equation like this, you can't use a of t, you actually have to use the derivative in the equation itself, and so that's what you need to have right there. That is your equation you're going to use. Okay? All right, let's look at the next question. Focus going on here. Bacteria in a certain culture increase at a rate proportional to the number present. So that's going to be key right there. If the number of bacteria doubles in 3 hours, in how many hours will the number of bacteria triple? So bacteria in a certain culture increase at a rate proportional to the number present. Okay? So what would that look like? Let's go ahead and take a look at this answer here, and you can see. So we're going to let B equal the number of bacteria, capital B. We want to write the differential way that describes the situation. So the rate, okay, the bacteria in a culture increase at a rate proportional to the number present. So the rate that B increases is proportional to the actual number in the dish, the population of the bacteria. So that's how that would be written right there. Little side note here, we're going to learn how to solve these things up in a coming lesson, but that's right now we're just learning how to write them from word problems. Some questions you'll see in the future. Get to it. May look like this, multiple choice. A rumor spreads among a population of n people at a rate proportional to the product of the number of people who have heard the rumor and the number of people who have not heard the rumor. If P denotes the number of people who have heard the rumor, which of the following differential equations could be used to model this situation with respect to time where k is a positive constant. So you break it down. When you use that frame up here, the proportional to, the first part is the y part, and the second part would be the x part up in our y is proportional to x. So let's take a look at that and see if we can figure this out. The rumor spreads among a population of n people at a rate proportional to the product of the number of people who have heard the rumor and the number of people who have not heard the rumor. Okay? P denotes the number of people who have heard the rumor. So this is the number of people we have. Okay? And P is the number of people who have heard the rumor. You've got to have a constant of variation. You'll see all these have a K in it. All of them have dP, dt. So those are all similar in that fashion. So that is the rate at which people hear a rumor, correct? So what I need now is a product of the number of people who have heard the rumor and the number of people who have not heard the rumor. So how would I determine those two things? Okay, this is the number of people we have. This is the number of people who have heard the rumor. So n minus p must be the people who have not heard the rumor. So we need an n minus p in our problem. And I think that gives us our answer. Let me pull off the answer choice here. And we get the answer of B. The number of people who have heard the rumor, and this is the number of people who have not heard the rumor, and that is a product of those. Okay? So let's take a look at another example we have, or another topic we have that we'll be asked to do. Pull it over here. And another thing we'll be asked to do at some point, probably in our tests and stuff, is to verify solutions for differential equations. So in previous subjects, classes before this one, if we were asked to verify a solution, okay, that means we're going to check our answer, basically, and we use substitution to do that. So if I want to verify that x equals 3 is a solution to this equation over here, then what I do is I simply plug in 3 and see if it works. If I get a true statement, then yes, it was a solution. The same thing applies with differential equations. Okay? So let me go ahead and take a look at an example here that I have. How do I verify that this is a solution to this? So when you look at it, you can see clearly that my equation that I'm trying to plug into has a second derivative and then just the function itself. So that means I have to first find the second derivative of this. Okay? So we need to find y double prime. So start with the first one, y prime, and take the derivative of this with respect to x. And as you do, you're going to get negative sine of 2x times the 2, and then 6 the cosine of 2x times the 2. You can clean that up to make finding the second derivative a little bit easier. I have a 2, a negative, and a 4. That gives me negative 8 sine of 2x. Here I have a 2 and a 6. So that gives me the 12 cosine of 2x. This is the first derivative, but I need the second derivative, so I need to take the derivative of that again. Okay? So here's our negative 8 cosine of 2x times the 2. Here's my 12 negative sine of 2x times the 2. And then we clean this up because we're going to be using it. So we have a 2, so negative 16 cosine of 2x. Here we have 2, negative, and 12, so that's negative 24 sine of 2x. So we're going to take this quantity right here and this quantity right here and substitute them into that equation and see if it works. Okay? So we have y double prime, so negative 16 cosine of 2x minus 24 sine of 2x. Plus, and I didn't give myself enough room, see if I can squeeze it in there, 4, and then here we have 4 cosine of 2x, 6 sine of 2x. And does that equal 0? So distribute and look and see what we have. So I have a negative 16 cosine of 2x minus 24 sine of 2x plus 16 cosine of 2x plus 24 sine of 2x. And you can see clearly that everything is going to drop out and I get 0 equals 0. So yes, it is indeed a solution. Okay, so when you see something like that, that's what it means. Down here is another example, kind of walking through it a couple of times real quickly here. Determine whether the given function is a solution of the differential equation. And again, f double prime minus f equals 0. If this is f, does it work? Well, in all of these cases, I have to find the second derivative. So doing that real quickly here, f prime of x is the sine of x. F double prime of x is the cosine of x. So the cosine of x minus f, which is negative cosine of x, this does not equal 0 because it's going to become 2 cosine of x's, and so this is no, it is not. It is not a solution. Here we have this function right here. So what is f prime? Is going to be 2 e to the negative x times negative 1, which is simply negative 2 e to the negative x. And then the second derivative is going to be basically the same kind of thing again. It's going to have that negative 2, that times a negative 1, which means I'm back to 2 e to the negative x. Plug everything in. 2 e to the negative x minus 2 e to the negative x. That does indeed equal 0, so this one is a solution. And then what about this one over here where I have some generic constant k, and you can see it's pretty much the same thing. You'll have k e to the x, and the second derivative is k e to the x, and so yes, these will indeed be a solution. Okay, so that's basically how you verify things out. And let's just look at some variations of our problems that we might see on a test or something along those lines. Here the equation is a particular solution of which of the following differential equations. So we have all these equations down here, and so you look at the choices. This is my y. If it says it's a solution, I can then plug into these and see which one is the correct answer. So in doing so, the highest derivative I see in here is a second derivative, so I'm going to have to go do a second derivative of this function so I can see how those answers play out. So the first thing we're going to do is take and find y prime, and it's 2 e to the 6x times 6, derivative of that's 0, so that's gone. So this is going to be 12 e to the 6x. The second derivative then is 12 times 6, or this right here. And so what you do now, you have the y prime, you have y double prime, you have y. This is y if you need it. And you have all these over here, so you just pick one and start plugging in and see if you can find the one that's the solution for it. Okay? So I'm just going to start with the top one here. We might as well start with A. Plug this in. So I'm going to have a 12 e to the 6x minus 6 times 2 e to the 6x minus 5 minus 30. So is this a true statement? If you look closely, you can probably see already that this is indeed the answer. And so we have found the answer, luckily, on the first try. Okay? But if it did in the first one, then I go to the second one and I keep on going until I do find the right one. Okay? So our answer here is A. Okay? Let's take a look at any more examples, or maybe that was the last one. I believe that was the last one. So these are the different kinds of questions you may see. And That ends this video, and we will talk more in class.